So Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and a very pleasant day I bid to all. So my name is Alia Aisyah Binti Abdul Aziz, and today I would like to present my final year project. So my FYP title is Numerical Simulation of Vortex-Induced Vibration on piggyback pipeline with different gap ratios between the pipeline and the seabed. Next, let's look at the table of contents. So it is divided into four. First, we have the background. Second, we have the problem statement and objective. Third, we have methodology. And last but not least, we have expected result. So moving on to the background. So submarine pipelines are widely used in the offshore oil and gas engineering for transporting oil and gas products. Day by day, there has been an increase in the usage of numerous pipelines that come as a unit due to economic and technical factors, and one of them is called piggyback pipeline, which consists of two parallel spherical cylinders with different diameter. So in piggyback pipeline consists of two parallel spherical cylinders with different diameters. So the large pipe will transport oil and gas, while the small pipe will transport monitoring signal and oil displacement material. So this method reduces oil waste and reduces construction costs. So in the next slide, I want to show you guys about the configuration. So in this present study, flow around different configuration of piggyback pipeline close to a flat seabed has been investigated using CFD software, that is Alta AccuSolve. So the small pipe, we have the large pipeline, and also we have the seabed. Next is VIV. So in fluid dynamics, VIV are motion induced on the body interacting with external fluid flow and the periodic irregularities on this flow. So VIV often happens to pipeline, and this will result in high frequency stress reversal to the current flow. So in short, there are four important elements in my research. First is VIV, second is vortex shedding, and then we have Reynolds number, and last but not least is different configurations on piggyback pipelines. Moving on to the objective. My first objective is to determine the hydrodynamic forces of VIV on pipeline with different gap ratios between the pipeline and the seabed. Second, to investigate the amplitude of structural responses of a pipeline due to VIV with different gap ratios between the pipeline and also the seabed. Moving on to problem statement. So here, as we can see here, it is a very long problem statement. So in short, we can say that there are four problems that can occur from VIV. First, it can shorten the piggyback pipeline fatigue life and increase the risk of structural failure. Second is the cost of recovery to shore for repair. Third is a reduction in gas export flow rates. And fourth is the increasing time and cost for operation. So here in this video is the incident that happened in Gulf Mexico where the pipeline is leaking. So this is one of the few examples of why we don't want the pipeline to be damaged. Is because if it is damaged, things like this can happen, and it can cause us lives and casualties, and also it can endanger the environment. One of the examples that actually causes casualties is the Deepwater Horizon incident, and this is what we are trying to avoid. Is methodology. So here we have the flow of the research. First is starting point, pre-analysis, analysis, and then simulation, post-analysis, and the end. The case study consists of the diameter of the main pipeline, small pipeline, and other kind of configuration. So the next one is flow chart of methodology, which is in my pre-thesis, and also we have the 2D design of piggyback pipeline, which is in the pre-analysis stage, and also the 3D design. And last but not least, we have the mesh of the computational, which has been done in the CFD software, and this is the analysis phase. So moving on to expected result. So here, a series of two-dimensional numerical simulations of VIV of two circular cylinder with uneven diameter at a Reynolds number of 3.6 times 10 to the power of 6 near a horizontal plane wall will be performed. So constant mass ratio M equals to 10, gap ratio equals to 2, and spacing ratio equals to 0.2 are going to be kept during all of the simulations. So position of the small cylinder will be varied. For the case of static cylinder, the model is expected to perform reasonably well at Reynolds number 3.6 times 10 to the power of 6. The CD and CPB values should be showing good agreement with the other numerical studies and fall within the experimental results range. For the case of vibrating cylinder, at gap ratio of 2, the interaction of vortices shed from the large cylinder with the bottom boundary layer is expected to lead to bottom boundary layer roll out. The suppression mechanism of the vortex shedding from the bottom surface of the cylinder is expected to be present. So I think that is it. That concluded my presentation for today. I hope that everyone that watches this video can actually understand what I'm doing in my final year project. So thank you for listening and have a great day.